so I need it quiet. Okay, now, the thing is, yes.
Is over the point discontinuity?
That we're going to do that today. That's new. The slant asymptote is the only thing you were responsible for last night. Okay, on Friday we took some of these apart, and I had to follow this sheet. This is extremely important. Who doesn't have this? You grab one? Okay, now, this does not work like your normal polynomials because this is not continuous. There's something that causes a break throughout your graph. It's whatever happens in your denominator as of Friday. As of Friday, that's what we looked at. We said, okay, something's going on in the denominator, so I can't go through that asymptote. It's going to bounce away from it. Give me 1 second. Then yesterday, Monday, we did the same exact thing, but we threw another type of asymptote in there. It's called a slant asymptote. And if you take a look at your asymptotes, your horizontal asymptotes, when we check your horizontal asymptote, if we do not have a horizontal asymptote, then we check for a slant asymptote. The slant asymptote says if the degree in the numerator is 1 more than the degree in the denominator, then you have a slant asymptote. Now, also, we talked about most of your functions were looking like this. They were kind of like rounded off like this. A slant one is going to kind of do something different. It's going to kind of slant this. Now, when you find your slant asymptote, if you put that into your y2, you'll see where the slant asymptote helps the end behavior of your function. Because your asymptotes are what guides your end behaviors. Okay, so your slant asymptote is no different than a vertical or a horizontal. It's just slanted. And it follows your format of your line. Y equals mx plus b. Question, Torrance? Did I answer it? I just needed to wrap this whole thing together. Well, yes.
For the slant asymptote, it's always going to be in the form of like an equation?
Yes, because this. Now, let's walk through this one. We factored this, but we can't reduce anything. Today, we'll be able to reduce it and find a point of discontinuity, but I went through it one step at a time. So we followed your sheet. We said, okay, domain. The domain says, oh, I can't use a 4. Take it out of my domain. Then I got 2 vertical asymptotes. I'm following your sheet. After we factored, and we couldn't factor, we look at the zeros of your denominator. So we take this down here and we set it equal to 0. There's an asymptote. What this does is this. There's x equals 4. It says, when you go to do this, your function is not going to be able to pass through this. It's going to bounce off of this somewhere. It's going to guide the end of your function. This is what guides your end behaviors. Now, we got to your horizontal one. Your horizontal one says, on your sheet, take the highest degree in your numerator, which is a 2. Take the highest degree in your denominator, which is a 1, and compare those. Yes?
Where did you find your maximum?
I didn't get to that yet. You're going to have to change your window on this one.
Okay, because
you got to change your window.
It's not there.
Right, we're going to change your window. Now, we check the degree of your numerator. 2 is greater than 1. According to your list, you have no horizontal asymptote. Now, come down and check for a slant. A slant asymptote says, when your degree, didn't I give you one answer?
No, what you're working on.
Oh, what I'm working on over there. Okay. degree in your numerator is 1 more than the degree in your denominator. You have a slant asymptote. So this is the only time we synthetically divide. The only time on a rational. So we take out our 0, we divide it out, we ignore the remainder. This is going to be a y equals something. Well, when you have x2 over x1, or x3 over x2, what's left is plain old x1, right? So therefore, this is the equation of my line. Y equals mx plus b. I have a line, x plus 7. Now, if you put this physically in your calculator, it will give you a line that goes like this. So now, you see this right now. And Melisande says she can't find an x because your calculator's doing this. It's saying, okay, come down here. Where do you think the other part is? If I'm within this section, the other part is sitting up here, isn't it? Let your asymptotes help you. Isn't this going to guide my ends, my asymptote? So if you can't see this, what do you have to do to your y max? Raise it. Increase that window. Change your y max to 30. And then you'll be able to see it. The rest of this is the same as before. Locate your max. This is a max. Right here at A. This is my relative max. I do it the same way as before. Locate your min at B. This is my relative min. Now I know how to do this from before. I find all these to 3 decimal places. These change slightly when it comes to your intercepts. If you remember to your polynomials, we kept dividing. We don't do that on this one. We say to find your x-intercepts, take the zeros of your numerator, take these factors, and set them to 0. This is what we did on Friday. Monday it didn't change. We did this on Friday. Do you have the sheet? Okay, this is what's going to help you walk through each one of these. Now, your y-intercept, that stays the same. Just let x equal 0 and see what's left in there. Concave down, concave up, stays the same. This guy is concaving down. And your x values.
You ever gonna have an asymptote by itself, or you're always gonna have
Normally, if you have a slant, you probably have a vertical because it needs something else to like guide it. But if you have a slant, you will never have a horizontal. Because a horizontal says if you're greater, you have none in the numerator. And if we check a slant, we are greater in the numerator than the denominator by 1. So if there's a slant, there's no horizontal. Normally you have a vertical just so that it would figure out where the rest of the ends are supposed to go. Your asymptotes are kind of like, did you ever go bowling and use the bumpers to bless you? Did you ever use the bumpers in there? You know, like if when you're little, you keep rolling gutter balls. So you put the bumpers inside so it guides your ball so that it bounces off the bumpers. It never crosses into the gutter, does it? It gives it a guideline. That's kind of like what your asymptotes are doing. Your asymptote says, I want you to fit my graph right in between here. I want you to put my graph in here somewhere, I don't want to touch those bumpers because that will put me in the gutter. So these are my guidelines to get there. Now, your increasing, decreasing works the same. Your range is the one that you should wait until after your asymptotes and after your max and mins. Because now, my range, my y will go from here to this y, which is this y right here, from negative infinity to 2.515. Then, it won't start up again until this y, which is this. And it will go on to infinity. Okay? So that's what my range is. It didn't change either, but wait until you get all your other parts down to do your range. Okay? So all we added Monday was this slant asymptote. Okay? What honestly helps you guys is this sheet. Without the sheet, I even forget which comes next. Okay? Now I had to hold off on number 2. And number 2, everything works the same, but number 2 has a condition that we're going to look at today. God bless you. Number 2 has a condition called point of discontinuity. That's what we're going to look at today. Everything else obviously works the same. So all we're going to add is your point of discontinuity. Number 3 was a nice, small little one. Looked nice. You can almost see where your asymptotes go when you graph them. We have a vertical asymptote. Take your denominator, set this equal to 0. Take that restriction out of your domain. Your vertical asymptote says after you factor, it's the zeros of your denominator. So that's the same as this, right? Horizontal says take the highest exponent in the numerator. Well, since there is none, I have x to the 0. Right? Isn't x to the 0 1? So I technically have x to the 0 over x to the 1. My degree in my numerator is less than the degree in the denominator. It's right here in the middle. You have to follow this. This one says you automatically get the x-axis. Y is equal to 0. You automatically get this asymptote. If you have a horizontal, you do not have a slant. Because then it can't be the top is less than the bottom, right? So the top is greater than the bottom. Now, zeros of your numerator. You have no x values in your numerator. Therefore, you have no x-intercepts. Doesn't your graph have no x-intercepts? Your y-intercept. So it's -2. Get rid of this guy. -2 over 5. There's your y-intercept. Now, once you know that you cannot use this y of 0, take that out of your range. You can use all the other y's except for 0. Your domain restriction is always going to be whatever is in your denominator, even before you factor or do anything else. Your vertical asymptote will be after you factor it. We're going to see that today. Okay? And the rest, guys, concavities, they work the same. It's the same as we did before, concave down. This is considered a concave down. This guy's considered a concave up. Number 4, you could not factor your numerator. So here's your zeros in your denominator. Get this out. There's your domain restriction, and it was also your vertical asymptote. Your horizontal one says it's x2 over x1. So you have none according to this sheet. Now, when you have no horizontal asymptote, you check for a slant. Your slant says the degree in the numerator is 1 more than the degree in the denominator. Yep. We have no horizontal. When we have no horizontal, we check for a slant. Because they can't exist at the same time. Your slant on the bottom says if your degree in the numerator, which is a 2, the degree is your highest exponent, is 1 more than the degree in the denominator, which is a 1. So isn't 2 1 more than 1?
Yeah.
Now we have a slant. To find the slant is when we do synthetic division. Take your zeros and divide it out. This right here, this is going to be y equals, and this is x to the 1, because x2 over x1 starts with x to the 1. There's your line, y equals x. If you put this in your y2, it's going to actually give you this line. You will see your graph. Use that as an end behavior. If your graph cut through that, you found the wrong line. So it's a good one to put your graph in there. You can't put your vertical asymptotes in there because it's a y equal. You can put your horizontal asymptotes in there because they're y equals. But your x equals you can't put in there. your slant and your horizontals you can put in your calculator. And it's a good thing to do it. You kind of see them. The 83s, the black calculators, yeah, they sometimes put the asymptotes in there. The verticals. Yeah. So you have to kind of put your slant ones in there. They do put the verticals, like pieces of them.
After the meetings, for your range, and then
My range?
Yeah.
The range, we had to wait till we found your max and your min. So this max at A, this relative max, went all the way up to -2. So we went from negative infinity to -2. Then we didn't use any y's in here. We started again with this y, which was 6. And we did 6 to infinity. Clarence?
On the footage, you don't show the asymptotes on the graph, you take off.
The asymptotes is what helps you guide your graph. So without the asymptotes, it's kind of hard to see where are these things going. Like you may loop it through in a different spot. It's best to keep your asymptotes there. With your asymptotes, you can pretty much draw it, and you'll see if you weren't able to see this part up here, you'll know you have to change your window to see it. Okay, and go ahead.
so we should basically
You should do. I would do my asymptotes before I do any graphing, because watch what happens. Here's my vertical asymptote, x is 2. Here's my line, my slanted x, y equals x. Look where my graph has to go. It has to go right in here and right in here. So this guy, there's my sketch. This guy, there's my sketch. It just gives me the guideline for my graph. Okay. Now, the last one, you could factor the top, but we couldn't reduce it. In the denominator, that gives me a domain restriction and your vertical asymptote. Your horizontal asymptote says degree of the numerator is 2, degree in the denominator is 1. When the degree in the numerator is greater than the degree in the denominator, we don't have one, but we check for a slant. As long as it's 1 more, we have a slant. If it was x4 over x2, we don't have a slant. So we divide it out, and here's your slant asymptote. If you even put that in your calculator in your y2, it shows you. It'll give you the guideline for your graph. Do your max and your min. Again, down here, if you graph this, now this is what I'm saying. If I go to graph this, here's my x equals -2. Here's my 4x minus 8. I'm crossing at the -8, right? I'm crossing at the -8, and I'm a +4. So it's somewhere over here. And I see this over here somewhere. I know there's a piece down here. So if I can't see it on my graph, I have to push my window down. I have to move my y min down until I can see it. Otherwise, you can't do a max or a min on it, right? If it doesn't show up on your screen. Okay. Now. Yes.
How would you get your max and your min
You
on that graph?
right off your calculator. Do second calc, do your max. Do second calc, do your min. Same as we did before. Everything else is
I had a hard
same.
time finding the maximum minimums for those.
Because you had to change your windows. Because you can't see it on your graph, you have to change your window. Look at how far down this guy is. It's way down here. See where the y is? You have to change your y min to like -50.
No, I mean, not necessarily for that one, but just for example, just any one of them. I have a hard time.
Use your cursor to go to the left, to go to the right.
Yeah, that's actually what I did, and but it still wouldn't give me the max or the min.
Really?
Yeah.
That's weird. Okay. Let's see if we can hit, guys. Okay. Let's see if we can hit your point of discontinuity in 2 minutes. Okay. Now, in yesterday's assignment, we had this one. Now I'm going to show you where your point of discontinuity is and what it means. Hmm? Yes. Because we haven't seen that yet, right? We keep saying factor, factor, but we haven't been able to reduce anything. Now, let's factor your numerator. What can we factor your numerator into?
X minus 2 equals 3.
X minus minus.
Oh, wow.
Up 2. Okay, now, in the bottom, let's factor out an x first. Okay, so what does that factor into? This is an x plus an x minus. Minus 3 plus 2. Now, this is where we say factor, and what can we reduce out of here? X minus 3. Now, hold on to that, circle that, and write what's left. X minus 2 over x, x plus 2. This is what's factored form is left. We have to refactor it. This guy right here, set it equal to 0. This is your point of discontinuity. Okay, now let me explain what this means. Your graph says this. Here's your vertical asymptote. X is 0, x is negative 2. Watch. Here's my x is 0, my x is negative 2, my x is 0. Your graph, and we're going to do the rest, is going to go like this, it's going to go like this somewhere, and it's going to go like this. Now, just give me 1 second. In your graph, your x at the 0 will say error. At the negative 2 will say error. At the 3 will say error, but I don't have this. It looks like it wrote over this. There's one little tiny point when x is 3 that gets removed from this graph. But your calculator looks like it writes over it. Now, all I want you to do...
Good afternoon. Today is a B day. To Miss Cadena Guidance, Marquise